Hello everyone. Can you hear me? Just let me know in the chat if you can hear me, so we can start. Brilliant. Okay, fantastic. Right. So we've marked pretty much 99% of the papers. Don't worry if you don't see your grades. We don't publish your grades, but you might have seen your comments on your work. We are analyzing hard. It looks like that the pass grade will not be far off 50%, which is very nice, which is in line with what we had last year. Yeah, we don't know until we analyze all pieces of data. This will take a few more days, so don't worry. Bear with me. But if you are well above 50%, it's almost guaranteed. Let's say if you got like 60 and 70, most likely you're in. Okay, I can't promise anything, but not far off from 50, maybe even 55, 60, and you'll be in. But okay, not promising anything. Overall, we it looks like we have more than 50% will be accepted. More than 50% of students that have submitted work will be accepted. Okay, so another piece of great news. So I'm thinking 60% will be. I don't have the numbers. It's about yeah, I think it's 372 and 200 will be accepted. So not, yeah, approximately 200. Initially we planned 150. We've increased that to 200. If your PDF has been uploaded to Google Classroom, it will be marked. It's we won't miss a single one. Okay, so don't worry. And as long as it's readable, if you don't have a comment saying I cannot read this, then it's you're on good. Okay. I'll share my screen and we'll do some kinematics today. So kinematics, equations of motion. And the first question, it's not very difficult, but it's quite fun. Just I found it quite fun anyways. So we have a photograph of a plane and it's smudged. And it's smudged because the plane is moving. Because what happens is the camera opens the shutter and then closes the shutter. And in that time, while the shutter is open and then closed, the plane has moved some distance. And the shutter speed is 0.1 seconds. So the camera is open for 0.1 seconds and then closes again. Doesn't happen instantly because the light has to physically get into the camera and activate the light sensitive element in the camera called CCD. Yes, charge coupling device. You have photoelectric effect that bumps electrons out of the charge coupling device, and this charge is registered and the camera analyzes the picture. Well, the shutter is open for 0.1 seconds and then closed. In that time, the plane has moved. And all we need is to figure out how far it moved. So from the picture, we can see that it moved, well, this distance. So what is this distance? Well, we can do a scaled diagram, but let's look what we're given. Length of a plane. That's something you can look up in online. If you take a picture of a plane yourself and you look up the length of the plane, it will tell you. is 30 meters. So this, the length of the plane is 30 meters. The length of the nose part is 10 meters. And on the photograph, it's 1 centimeter. So this is how we get the scale. So this is 10 meters. So if 1 centimeter is 10 meters, then the whole picture, the whole shadow of the airplane from here to here is 50 meters. 50 meters. And then it says the length of the airplane is 30 meters. So the actual plane is just this bit. So that's 30 meters. That means the plane has traveled 20 meters. Does that make sense? Does this make sense that the plane has traveled 20 meters? 1 for yes, 0 for no, please. Okay. Brilliant. Because the length of the plane is 30 meters, but on the picture it's 50 meters. That means it has traveled 20. So it's 20 meters in 0.1 seconds, and very easy, we get 200 meters per second. Now this is the cruise speed of a plane, so probably this, I took this stock picture. It's not a real picture. The measurements are not real, because when landing, a plane goes at about 50 meters per second. Okay, so much slower than what we have. 200 meters per second is the cruise speed at altitude. Anyways, quite a nice thing to do. So you, just as well, you can take a picture of a car and figure out how fast the car is going by just taking measurements of the car or anything. Okay, so just like that. Right, and let's get to slightly harder questions. A passenger is late for a train and runs towards it along the platform. So what do we have? So we have a platform, and then there is the train. There's the train. I don't know. There's the train. Runs towards. And the passenger is running. The passenger is running at 3 meters per second. 3 meters per second. Running noises. And when the distance is 12.5 meters, when the distance is 12.5 meters to the door of the train, 12.5, the train starts to accelerate. Train starts to accelerate at 0.2 meters per second squared. When will the passenger catch up with the back of the train? How far would the train? I'm sorry for my spelling. How far? That's embarrassing. How far would the train have traveled? The passenger is late for a train and runs towards it along the platform. Right. Yeah. The door. Nowadays, the doors of trains are the doors of trains are automatic, and it used to be that they were manual. So if you run to the train, you can actually open the door and jump in. Not that it's very safe to do, and not that I've never done it. But that's that. And right. So, well, there are many different ways we can do it. Let's do it very formally by writing the equations of motion. The equation of motion is very similar to a Suvat equation, but the main purpose of an equation of motion, it tells you the coordinate of the person at any given time. So the equation of motion is x as a function of time. Okay, tells you the position of a body at any given time. Now, this is called the main problem of mechanics. The main problem of mechanics is to tell where things are at any given time. And this is quite important. Like, if you are in charge of the International Space Station, you want to know where the station is at any given time. Okay? So the Suvat equation is pretty much the same thing, but the purpose of a Suvat equation is not always obvious. It's not it's finding the unknown value given some values, right? But the ultimate goal of mechanics is to tell where things are at any given time. And if we have the person is starting from, let's say, starting from 0, and this is the x-axis, x of the person with respect to time is simply 3 multiplied by t. Okay, because when t is 0, the person is at 0. When t is 1, the person is at 3 meters. When t is 2, the person is at 6 meters, etc., 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 etc. Exactly. Now, the of the train, the position of the train when it's uniformly accelerating, it could be written like this: the initial position plus the initial velocity u multiplied by time plus 1/2 acceleration multiplied by time squared. Right. Acceleration by time. We can prove this. Like, why is this so? Well, let's say we have acceleration. We know that velocity is the integral of acceleration with respect to time. The integral, a is a constant, so it's at plus c. But c is the initial velocity, so it's initial velocity plus at. Yeah, because c is initial velocity. Now, the displacement is the integral of velocity with respect to time, which is the integral of u plus at dt, which is ut plus 1/2 at squared plus the initial position plus c, where c is the initial position. And therefore, we have x0 plus ut plus 1/2 at squared. If you haven't done integration, don't worry, you'll get there. But if you have done integration, I hope you can appreciate that. Type 1 if you understand what I did here, type 0 if you haven't done integration yet. Oh, brilliant. Okay, very nice. Okay, so this is the equation of motion for a uniformly accelerated object. And all we need is we need to substitute the values. So x of t is the initial position, which is 12.5, plus u, which is 0, multiplied by time, plus 1/2, acceleration is 0.2 t squared. And we have train, x train, with respect to time, is 12.5 plus 0.1 t squared. And of course, when the passenger meets the train, they have to be x passenger is equal to x of the train. That means 3t has to equal to 12.5 plus 0.1 t squared. I'm going to be a bit lazy. I'm just going to use my calculator. It's a quadratic equation. There's nothing here. So it's 0.1 minus 3 and 12.5. Absolutely. So T1 is 25 seconds and T2 is 5 seconds. So there are two answers. How come there are two answers? How come there are two answers, and which answer do we need? Does anyone know? Exactly. The person, if the person keeps running, the person will run past the train, but since the train is accelerating, the train will then accelerate and then go past him again. Therefore, it's the person will go past the train twice. Now, obviously, we need the first one, because what happens is the speed of the train. The train is the initial speed, so initial speed plus AT. So it's AT, which is 0.2 t. So at 5 seconds, the train is going 0.2 times 5, which is 1 meter per second. And velocity at 25 is going to be 0.2 times 25 is going to be 5 meters per second. Now well, first of all, it's pointless running past the train and then waiting until the train catches up with you. And secondly, jumping into a train at 1 meter per second is relatively safe, whereas jumping into a train at 5 meters per second is definitely unsafe. So at t equals 5, the train is traveling at 1 meter per second. And how far does the train travel? We need x of 5. Yeah, because x train of 5 is equal to okay, well, we'll get there. So 12.5 plus 0.1 times 25. So 12.5 plus 0.1 times 25, which is 2.5, which is 15 meters. 15 meters. But that's from the starting point of the human, and the train has traveled. Delta x is x of 5 minus x of 0. So it's 15 minus 12.5. 15 minus 12.5, which is 2.5. 2.5 meters. So the train would only have traveled 2.5 meters and traveling at a speed of 0.1 meter per second. So, okay. Now, these two graphs, we can solve this graphically as well. So let's do my favorite Desmos. So x x is equal to 3t, and x is equal to 12.5 plus 0.1 t squared. All right. And you can see no, doesn't like it. Okay. Well, anyway, we can ignore the bottom bit, and we can see that this is the equation of motion of the this is the graph of motion of the train, the blue one, and the red one is the person running. So the person is running at constant speed, and they catch up with the train twice when okay, I need to do it the other way around. Why? Sorry. 3x doesn't like it. Okay, that's better. All right. Person catches up with the train twice. So when t is 5 and when t is 25. And then the train speeds away from the person. So hope that makes sense. And I'm just going to sketch that. So this is the position. This is time. So we have the person running, and then the train. Okay, so that's 5 seconds, and then 25 seconds. It's accelerating. Okay, so hope that question makes sense. I just really want to point out that this is a huge deal. Like this equation of motion. Just yes, keep in mind whenever you're asked to find the equation of motion, it is this. And this equation of motion is a Suvat equation, because the Suvat equation S is equal to ut plus 1/2 at squared. But then by definition, we know that S is x minus x0, the current position minus the initial position, because that's the displacement vector is the final position minus initial position. So we have x minus x0 equals ut plus 1/2 at squared. And we have x is equal to x0 plus ut plus 1/2 at squared. Oh, R is the same thing. It's just Suvat is a consequence of the equations of motion. Yes, Suvat is a consequence of equations of motion. And it's very useful if you can derive the Suvat equations. And it goes like this. So let's say you have. Okay, you know what? I'll if we have time, I'll do the derivation of Suvat, but there are other things I would like to go through. Sorry about that. Okay. Problem 3. This is a PAT problem from 2006. The graph below shows, and actually they love this question on Oxford interviews, by the way. It's similar questions, not the exact same, of course. The graph below shows the velocity of a rocket as a function of time. What happened at x? Anyone? What happens at X? Yes, Y. Rocket stopped accelerating, correct. Its fuel got ejected. What do you mean by fuel got ejected? Next thruster engaged. I don't see that happening. It exits the atmosphere, does not need escape velocity. Exits the atmosphere, but why does the velocity comes to a stop? Definitely doesn't stop because the velocity is 2000. Detached accelerated runs out of fuel. Yes, thank you. It runs out of fuel. At X, it runs out of fuel. Out of fuel. Now, it starts to decelerate. Now, the likely scenario is not because of the air resistance. It accelerates because of gravity. Like, yeah, you're flying up, you run out of fuel, you start slowing down. Because the uniform, if it was due to air resistance, it would be more like this. Like this. But because it's a straight line, this tells us that the deceleration is constant. And a constant deceleration means a constant force, and air resistance is not a constant force. Air resistance depends on the speed. So it's more likely gravity, but we don't know the specifics, so it's a guess that it's gravity. When the acceleration of the rocket a maximum, so just an explanation for this. Okay, so when is it the maximum? When the tangent is the steepest. Well done. Yes. The tangent definitely shows you the acceleration. Acceleration is the gradient. Acceleration is the gradient. And therefore it is the steepest between 50 and 60. 50, 60. Why do you think it is? Elliot, yes, thank you. Just before X. Yes, because it almost ran out of fuel. It has the lowest mass. And we know that acceleration is force divided by mass. So mass is the lowest mass just before X. Just before running out of fuel. Describe the subsequent motion of the rocket. Well, if it's going to be the velocity, so I'm just going to move that. That won't do the trick. The subsequent motion of the rocket is that it will carry on decelerating. What happens at A? Anyone? It stops. Well done. Yes. A lot of people say it hits the ground. No, it reaches maximum height. So at A is the maximum height. And how would we find? Well, when it hits the ground, obviously the speed drops to zero. The speed drops to zero. So how would we find this thing? Yeah, exactly, the same area. So we have area 1 and area 2, and they have to be the same. In order, B hits the ground, As accelerating, then decelerating, then accelerating downwards, and then stops as it hits the ground. And these two areas have to be the same because the area is the displacement. Area is the displacement. How in principle would you determine the maximum height reached by the rocket? Well, that would be the area A1. A1 is the maximum height. Area A1, maximum height. A1. So you can just physically do this from the graph. Just count the squares, or find a function that fits and then integrate it. Okay. All right, we're going quite fast. Okay, getting to harder questions. A stone is launched at an angle of 30 degrees to the horizontal from the top of a 30-degree inclined slope. Now, so one of this question is, well, a very similar question is on your assignment. So if you've seen the assignment, you've seen that there's a question like that. So there's a slope. There's a slope. There's a 30-degree slope. So that's 30 degrees, and it's shot horizontally. So we have a horizontal. Oh, sorry, it's an angle of 30 degrees to the horizontal. Right, sorry. So a projectile is shot at an angle of 30 degrees to the horizontal from a 30-degree slope. Okay. I think in the assignment is shot horizontally. So this makes it slightly harder. So you can predict that the stone goes like this. And the question is, how far, so this is 20 meters per second, how far down the slope will it land? So we need to find L. It's shot from the top of the slope. So I think that kind of indicates that, yes, the meeting is recorded. Must be recorded, yes. It is, but so how do you go about this problem? Well, you just try to make it less confusing, because having it find the vertical component. But if you do the vertical component, that doesn't really doesn't do the trick. You can split into vertical and horizontal components, but the problem with that is the equations are going to be really complicated, and L, the distance, will have both horizontal and vertical components as well. So it's not ideal. What we need to do, well, first we need to realize that there's a gravity. There's the acceleration due to gravity, which is G. We need to appreciate that you can put the x-axis along the slope. And this is what you always do. You put the x-axis along the slope, and you put the y-axis perpendicular to the slope. And let's draw this situation in the new reality. So this is a tilted universe of some sort. And in this universe, the projectile is shot at a 60-degree angle rather than 30-degree angle at a speed of 20, and the angle is 60 degrees. And the distance is purely on L. Now this is Y, this is X. All right, Robert, it does not matter if you use 9.8, 9.81, or 10. As long as you're clear what you're using as the approximation, you're fine. It does not matter. Right, but then we need to appreciate that the acceleration is not vertical anymore. The acceleration is sideways. So the acceleration is like this. So the downwards component, and because you've done such an amazing job with the first assignment, you have the downwards component of the acceleration and the horizontal component of acceleration. And the horizontal component of acceleration is g sine 30 degrees, g sine 30, and g cos 30. All right, and now we write the equations of motion. So x of time is equal to initial position, which is 0 and 0. Okay, let's make it obvious. x0 plus the initial velocity, which is vx, or ux, technically t. Now it is accelerating along x, so it's accelerating along x, and this is the acceleration. So plus a half gx the times t squared. So x of t is x0, which is 0, plus horizontal velocity is 20 cos 60, 20 cos 60 t, plus a half times gx, which is g sine 30, g sine 30. I'm going to use g as 10 just for simplicity. G is 10 newtons per kilogram. G sine 30 multiplied by t squared. So x of t is cos 60 is a half 10t. 10t plus a half times 5 times sine 30. Sine 30 is a half, so 2.5. 2.5 t squared. All right, that's the horizontal equation of for x. And now we have the vertical y of t. It's again y0 plus the uy t plus 1/2 gy t squared. Okay, so here we need to be careful with the directions. So y of t is y0, which is 0, or initial velocity, so 20 times sine 60 t plus, minus, because it's downwards, minus a half gy cos 30 t squared. This is the equation I'm using. I mean, this is a consequence of a Suvat equation. right. Well, I mean, look, the equation I'm using is this. R of t is equal to R0 plus the initial velocity times time plus 1/2 acceleration times t squared. But then we split that into components, and we know that r is xt and yt. That's the vector rt plus x0, y0 plus ux, uy multiplied by t plus 1/2 multiplied by ax, ay multiplied by t squared. And if you take the top line is this. The top line of this is this. And the bottom line of this is this. So it's two equations of motion. It just really helps if you always start from these equations. It really helps you to understand. And when you go with harder problems, you'll be much more confident if you learn it this way. So y of t is equal to 20 sine 60. So it's 10 square root of 3. 10 square root of 3t minus 1/2 g sine 30. So g is 10, 10 2, 5, 2.5 square root of 3 t squared. Now, when it hits the surface at this point, y is 0. So y of t has to be 0. So 10 square root of 3 t minus 2.5 t squared square root of 3 equals 0. So square root of 3 cancel by square root of 3. Divide by 2.5, that's 4. 4t minus t squared equals 0. t minus 4 equals 0. So t equals 0 or t equals 4. Now, why do we have t equals 0? Well, because when t is 0, y is 0 because it's on the ground. Well, on the surface. So t is 4. T is 4. And to find L when t is 4, x is equal to L. Yeah, that's t equals 4. T equals 4 seconds. And this is t equals 0 seconds. When t equals 0, that's no use for us. That's pointless. So t is 4 when it hits the ground. Hits the ground when t is 4. And therefore, we just put that in. So we put that. So x of 4 is equal to 10 times 4 plus 2.5 times 4 squared, and that's equals to L. So L is equal to 40 plus 2.5 times 4, that's 2.5 times 4 squared, so that's 2.5 times 4, which is 10 times 4 is 40. The answer is 80 meters. 80 meters down the slope. Now, what you will need to do in the assignment, you just don't have any numbers. It's a very similar problem, but you don't have numbers, and your answer will be in terms of letters. So good luck. Problem 5. Any questions about problem 4? Okay. Problem 5. I really like this question because it's just because it's so counterintuitive. To reach B, find the time to reach B. B is here. B is here. Basically, what you have a vertically placed circle, like a hula hoop. Okay. And imagine you have a string from A to B. You have a string from A to B with no friction, and you have a small mass which is allowed to slide from A to B with no friction. Okay. And you need to find how long it takes. How long it takes to slide from A to B with no friction. Okay, so how do we go about this problem? Well, first, it would be helpful to find the acceleration, or the length. The length. Okay, Robert. Yeah. Okay. I'll actually go through that the rope question after this one, and but also when you're assigned a tutor, you can talk to them. They'll explain to you as well. Zoom. Yes. Well, I'm not sure. I think you just click somewhere on your name and you can change it. Yeah, I right click on, for me, I right click on my face and press rename. Yeah. Okay, so we need to find the distance traveled and we need to find the acceleration. Acceleration is going to be quite obvious because if you're on a slope, on an inclined slope, you need the component of g along that slope. So you split the g into components, and this is g, and this is g g cos alpha. Let me double check that. So if we reduce that, this angle reduces. Yes, that's alpha. So that's alpha. So g, this is g cos alpha. This is g sine alpha. Sine alpha. So acceleration along this acceleration is going to be g cos alpha. Acceleration g cos alpha. Brilliant. Now we need to find L, the length. Well, this is actually super easy because if we draw a triangle like this, let's say AM is the diameter. And if AM is the diameter, then this angle is 90 degrees. So L has to be double radius multiplied by cos alpha. Okay, double radius times cos alpha. And then we just write the equation. The x is equal to x0 plus initial velocity times time plus a half at squared. So the displacement is L, the initial displacement is 0, the initial velocity is 0, plus a half times acceleration, which is g cos alpha, multiplied by t squared. So, and L, we've established that there's double the radius of the hula hoop times cos alpha equals a half g cos alpha t squared. Cos alpha cancels, 2r becomes 4r divided by g. That's equal to t squared. So the time is equal to 2 square root of r divided by g. Why is AM perpendicular to BM? It's not. AM is not perpendicular. AB is perpendicular to BM. Okay. Yes, it's one of the circle theorems. You can look it up. X0 does represent the initial displacement. X0 is the same as x of 0. Because if you plug in 0 instead of t, you get x equals x0, because these are zeros. Does that make sense, Arman? If you put t equals 0 into this equation, you're left with x equals x0. Okay. And you get the time. And interestingly enough, the time, we have found the time for an arbitrary angle alpha. So alpha can be anything. So if alpha changes, the time does not change. This is the beautiful consequence of that. If alpha changes, time does not change. So that means that going from A to B takes the same time as going from A to C, and as going from A to D, and from A to M, if the string was vertical, because the distance is greater, but you go with a faster speed. And if you go from A to I don't know, E, which is really, really close, no matter how close it is, because AE is almost horizontal, it will go really, really slowly, and it will reach E at exactly at the same time as it would reach M. So these, yeah, this is a beautiful problem in a way, and yeah, so okay, r is 2 meters, so 2 divided by 10, 0.5 to, well, it's a numerical answer, but who cares about the numerical answer? I mean, you could find the answer here. 4 meters. Okay. Is L always perpendicular to BM? Yes, because if you have a semicircle, it's an angle in a semicircle. It's the angle in a semicircle. It's a circle theorem. Okay, and it has a beautiful proof, I'd say. You start with saying, you know this, right? You know this circle theorem. And you know that if this is alpha, sorry, if this is alpha, this is 2 alpha, right? So if you have a big angle, which is really big, so if this is 180, this is going to be 90. And of course, 180 looks slightly different to that. Okay, so if this is a straight line, this is 90 degrees. This is GCSE stuff, so it doesn't matter which exam board you do. You should know this. And yeah. Okay, problem 6. Oh, so I did promise to go through the rope problem. It's really quick. So look, you have a rope hanging, and you have T1 and T2. So T1, T2, and let's say this is T1 sine alpha, T1 cos alpha, T2 sine alpha, sine beta, sorry, sine beta, T2 cos beta. Now we cut the rope in half, and we have the left-hand side. You have the same forces, T1. You have T3, let's call it T3, and you have the gravity, M1G. Okay, and then you have M1G. M1G is equal to T1 cos alpha. And similarly for the second piece of rope, you have T3 here, T3, you have T2, and you have M2G, and then equating the vertical forces, because T3 is horizontal, so the vertical forces, M2G is equal to T2 cos beta. And then you just compare them. You compare M1 and M2 because you know T1, you know alpha, you know T2, you know beta, and all you need is to work out the masses from there. Or if you might just need the ratio of masses, so you just divide them together. Okay, so M2 to M1 is going to be T2 cos beta divided by T1 cos alpha. And T2 and ratio of T2 and T1 is you already know from the previous problem. Okay, problem 6. A wheel of radius r is rolling along a road. A small piece of dirt detaches from the wheel at A and lands at the exact same location after one complete circle. Actually, it doesn't specify that it's one complete circle. So we'll just keep in mind, so maybe the wheel has made several rotations before the piece of dirt lands. Okay. So we need to analyze what's happening at A. So this is point A. Now the wheel is moving horizontally with a speed v. But it also is rotating. Look, the whole wheel is traveling at velocity v, but also each part of the wheel is traveling clockwise. So A is traveling to the right because the whole wheel is moving, but it is also traveling upwards with the same speed, v. So the total speed, total velocity, sorry, of A, and let's call it u, and by geometry, you know, it's a square and it's the diagonal of a square, so it's square root of 2v. Okay. Now, A, it's projectile motion. It's projectile motion, and for the piece of dirt, the dirt is a projectile. And we can just do it like this. So this is A, and this is A prime, and it goes like this. How do you know that the horizontal and vertical components are equal? Well, this should be intuitively clear. Okay. This should be intuitively clear. What's the best way to put it? So let's say so how do we know? So basically what you're asking, no, this is a very good question. And I was hoping nobody would ask it, so I don't have to explain. I'm kidding. Yes, I'm saying that this velocity v, and v, and v is the same. And when the wheel is rolling, and it's the same to this v. So v1, 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 v2 is the same. So we want to say that v1 has to equal to v2. Okay. Oh, I mean, it's not obvious that they are the same, but you can say that one rotation, time for one rotation, rotation is t is equal to 2 pi r is the distance traveled divided by v1, time for one rotation. And how far it travels in that time, v2 times t. But because it also travels v2 times t, the distance it travels in that time. Yeah, it travels this distance in that time, which should be equal to 2 pi r as well. Okay, so 2 pi r, and so we place that here. So 2 pi r is v2t. So t is equal to 2 pi r divided by v1, which is equal to v2t divided by v1. And we have t is equal to v2t divided by v1. T cancels. We have 1 equals to v2 divided by v1. And we have v1 equals to v2. Yes, Elliot, that's another way to put it. Okay, the bottom of the wheel has to be stationary on the ground. That's a very good explanation. As well, maybe I like your explanation better. I decided to go with this one. Just yeah, in hopes that it would be easier to understand. But the bottom of the wheel is stationary, therefore, because the bottom of the wheel is moving left, but the middle of the wheel is moving right with speed v, they have to be the same. Anyways, the dirt is a projectile, so the angle is 45 degrees because it must be 45 degrees. 45 degrees, and the speed is square root of 2 v, where v is the speed of the wheel. Now the distance traveled, so we need the vertical displacement. So y is equal to y0 plus uyt plus 1/2 at squared. So we're already familiar with this. So we know that the displacement is 0 because it goes from A to A. So the height does not change. It's on the same vertical line, which is 0 plus square root of 2 v. Oh no, the vertical velocity is v. We don't need just v. The vertical velocity is v t minus 1/2 gt squared. And from here, we can deduce that 2v minus gt equals 0. T is equal to 2v divided by g. That's going to be, this will come in handy. That's the time of flight. That's the time of flight, which is 2v divided by g. Right. The horizontal displacement, so x is equal to vx, the horizontal velocity times time, and the horizontal velocity is also v times time, which is 2v divided by g, which is equal to 2v squared divided by g. And we know that the wheel, that's the horizontal displacement. That's the length. That's the distance traveled, L. We know the wheel has to complete. The wheel completes n full rotations and travels L meters. All right, so L has to equal to 2 pi r n, because n is the number of rotations. N is the number of full rotations, and that's the distance. Because the circumference of the wheel is 2 pi r. 2 pi r times n is the distance traveled by the wheel. Therefore, we can equate that. We have 2 pi r n equating 2 pi r n must be equal to 2v squared divided by g. 2 cancels, and we have v is equal to pi r n g square root. That is the speed necessary for the wheel. And of course, get used to the answers in physics. The answers are very often given in letters as an expression rather than a number. So keep that in mind. Okay. You can do some calculations. You can substitute just for 1 rotation, radius 1 meter. You can find the speed at which you need to go, and then try it out with your bicycle. Okay. Problem 7. Now, problem 7 is one of the harder problems. I'm not going to go through the whole thing because otherwise I'll just give away the answer. I just want to explain how to look at this problem. Okay. Now, this is somewhat to do with the Doppler effect. This is somewhat to do with the Doppler effect. And there's lots of things. The plane is flying horizontally at speed 470 meters per second. A person hears a sound 21 seconds after the plane has flown off over their head. Find the altitude at which the plane is flying. Right, before we go into that, let's discuss the Doppler effect. Doppler effect. Or in more general, Doppler effect. Waves created by a moving source, which is probably what I really want to explain. I'm not really explaining the Doppler effect. I'll talk about the waves created by a moving source. So first of all, stationary source. Example, plane on the ground revving its engines ready to take off. Every plane before taking off does a power check. So they engage the brakes, yeah, and they switch on the engine and see if the engine works properly. Okay. And this is one of the pre-flight checks. This is what the pilots do before they take off. Also, if it's a short runway, they switch on the engine to full power, wait until the engines rev up, and then release the brakes, and they have a faster acceleration. So if the plane is heavy or the runway is short, they have a better chance of taking off. Okay. I mean, better chance. When I say better chance, it's a very rare occasion. It's like very rare occasion when the plane cannot take off. because it's overweight, because airplanes are the safest transport that we have. In regards to things like friction and air resistance, do we only deal with them if they are explicitly mentioned, or do we also need to consider these external factors, assuming we have enough info to find such things even when not mentioned in name? Look, if you're expected to give an answer as a formula or as a number, usually you ignore air resistance. Like in this assignment, in the one that you have, pretty much you ignore air resistance and friction. Okay, unless it's unless it is stated. It would be, we would say it's a rough surface, indicating that you need to account for friction, or we would say it's we would say account for air resistance if you need to take into account air resistance. Stationary, so by default, assume no friction, no air resistance. Stationary source, and the stationary source creates waves like this. So they originate from the stationary source, and they go outwards. These waves, they are spherical. It's not correct to call them circular because it's 3D. They are spherical waves, and they propagate in all directions. So that should be quite understandable. Okay. Now, a moving source of waves, moving source of waves. So, I hope you understand that the waves are traveling outwards. The waves are traveling outwards away from a stationary source. Now, if you have a moving source of waves, well, moving aircraft, there's a phenomena that the first wave, so this is the first wave, this is the second wave, this is the third wave, this is the fourth wave, okay? Because the wave number 1 was created before wave number 2, which was created before wave number 3, etc. Wave number 1 was created when the source was here. And wave number 1 looks like this. Wave number 1. Now, wave number 2, by the time wave number 2 was created, the source has moved. Okay, that's too much. When wave number 2 was created, the source has moved, and the center of wave number 2 is now here. So when wave number 2 was created, the source has moved. When wave number 3 was created, the source has moved again, and like this, and so on. So you can see this shape, and this, if you're standing here, the waves are shorter, and you're standing here, the waves are longer. But we're not talking about this. We're not really talking about the Doppler effect. That's not what I'm interested in. Now, moving source of waves, and then source moving faster, source moving faster than the waves. Right. When a source is moving faster than the waves, It's a very peculiar situation. When the first wave was created, the source was here. When the second wave was created, the source was already here. So it has moved. Is moving faster than the waves. And what you have is this cone, this supersonic cone. The supersonic cone. And you have seen this. I'm sure you have seen this. Wake of a boat. Here it is. Here's the cone. Here's the cone behind a boat, because the boat is traveling faster than the waves created by the boat. And this is the thing that you see. And here it is. Here it is. So okay. And sometimes you can see that wake here. This is just a lucky, because of the humidity of the air, you can actually see a cloud forming in the shape, in the exact shape of the cone, of the Mach cone. And the thing is that if you draw this cone, because the plane is traveling faster than sound, if you're standing here, you will hear absolute silence. And if you're standing here, you will hear a very loud noise, very loud. Okay. And this is what's going on. So if you're standing on the ground, and the plane is above you and is flying faster than sound, it's creating this cone. And you will not hear anything until the cone reaches you. Okay? This is how the sound propagates. So you will hear the sound when the plane is here and the cone has reached you. Okay. And here, you just use clever geometry to work out what's what. Okay. Now, this is the point just directly above your head, and this, let's say this angle is alpha, which you'll need to find. Now this is the distance traveled by the sound. So this, sorry, by the plane. So it's VT, and this is the distance traveled by the sound in the same time, which is CT. CT. So we can say that sine alpha is equal to CT, the opposite, divided by VT, which is C divided by V. And then from here, you will need to work out the height. H. Height is this, is H. So I'll leave you to it. This is a completely geometrical problem. Okay. So I hope that makes sense. There are plenty of examples of how to do this. So there are videos, Mach cone, calculating. Yeah, so good luck with that. Okay. Finally, problem 8. Problem 8, 2 cars are traveling. This is the question about the drone and the anti-drone missile. It's exactly the same question. 2 cars are traveling in perpendicular paths. When car 1 is at O, car 2 is at a distance L0 from the intersection. Find the minimal distance between the cars. Well, we need to find the coordinates. So these are the paths of the cars. So let's say the car V2 is at X and V1 is at Y. The position of the car. No, actually, sorry. Let's not make it more complicated than we need to. Let's call this D2 and this is D1. Now D1 is the distance the car 1 travels. So D1 is in fact V1 multiplied by T, multiplied by time. Now D2 is, well, it's L0, D2 is L0 minus V2 times time. V2 times time. Now the distance between the cars, D is square root of D1 squared plus D2 squared by using Pythagoras theorem. So, I mean, if D is maximum, then D squared is maximum. So we can make our life easier working with D squared rather than working with D. D squared is D1 squared plus D2 squared. D1 squared is V1 T squared T1 squared plus D2, which is L0 squared minus 2L0 V2T plus V2 squared T squared. And then just doing magic of numbers. So it's V1 squared plus V2 squared times T squared minus 2L0 V2T plus L0 squared. Now, I'm really tempted to do differentiation here. And maybe that is the best way. Although I did ask you not to do differentiation in that particular problem. This is a quadratic. This is a quadratic, and to find the minimum value of the quadratic, you need to complete the square. Find the minimum value of the quadratic by completing the square. Find the minimum. Okay, this is a quadratic in terms of t. This is a quadratic in terms of t. Don't believe me? Plug in some values for yes. Find the minimum value of the quadratic by completing the square. Right. This is a fun okay, it is a fun exercise. Completing the square from this expression is a tough but very rewarding job. So please do that. I will alternatively use calculus. Okay. So what do we use? How do we use calculus? Well, we know that if something has a minimum value, if we differentiate that, the derivative will be 0. At minimum, derivative is 0. At minimum derivative is 0. And so we have find the derivative. d2 squared, the derivative of that is going to be 2 v1 squared plus v2 squared t. So because v1 squared plus v2 squared is a constant, so we just take the constant, we just differentiate t squared, which is 2t, minus 2L0 v2, that's on constants, minus 2L0 v2t. These are constant, no t, sorry. And L0 is a constant, so derivative of that is 0. So this has to be 0. And then we have t is equal to 2L0 v2 divided by v1 squared plus v2 squared. And then plug in t to get plug in. Oh, we missed the 2, which is L0 v2 divided by v1 squared plus 2 squared. Plug in the t to get d squared. Isn't v? No, v is not a function. v1 and v2 are constants, so they're not functions of v. Yes, absolutely. The minimum value of quadratic is given by minus d squared over 4a. Is that so? Is it? Discriminant over 4a. I really don't see how it is the minimum value. Okay, C minus, yes, that is more like it. C minus B squared over 4A. Yes, that is that is correct. Yeah, but not what you said. Okay, plug in the T to get D squared. So you get an expression. It's not the easiest one, but it's going to be so D squared is going to be V1 squared plus V2 squared multiplied by T squared, which is L0 V2 divided by V1 squared plus V2 squared. It's a really an accuracy exercise. Minus 2 L0 V2 T, which is L0 V2 divided by V1 squared plus V2 squared plus L0 squared. And then you simplify that to get D. I'll leave this to you. Okay. Yeah, sorry, didn't have time to do the SUAT derivation. Maybe next week. Okay. You should know by the end of this week. You should know your tutor. You should, if you should know if you're in, and if you're in, you should know your tutor. So yes. All right. So thanks for coming, and I'll see you again next week. You're welcome. Hope that helps. You will get an email. Yes, you will all get emails. And even if you get an email saying that, sorry, we did not find your work, you can reply to that email and say, and we'll locate that work. So don't worry. If you have submitted work and if it's decent quality, you will get in. Okay. Well, the minimum, it passes the threshold. Okay. Brain was fried on the last one. The last one is not that hard. It's just a lot of maths. Okay, we physicists, we don't like maths too much. I mean, especially when it's like this. We prefer more simple answers. That's why we always simplify things. Yeah, when we always round and simplify. Mohammed, well, it's going to be close to 50%. We don't know yet, but it looks like it's going to be close. Okay. So, and more than 50% of the applicants that sent in the work will get in. Okay, that's a definite. More than 50% will get in. Right. Okay. Equals pi equals 3. Square root g. I'm not sure what that means. Mohammed, pretty much 88%. If you got 88, if you got an average of 88%, you're in. Yes. I'd say if you got 60-60, most likely you're in. Okay, I cannot guarantee. I don't know the final numbers, but 60-60 will probably you get in. 50-50 maybe. So I cannot guarantee. All right. See you. Yes, you too.